Welcome to my basic machine learning tutorial. In this project, we'll use logistic regression to predict the price range of mobile phones. In just a few moments, we'll jump into hands-on coding where we'll implement logistic regression to classify mobile phones by their price range. We'll cover basics such as importing and overviewing data, analyzing data using univariate and multivariate methods, understand insights from EDA, build and evaluate models. We'll get a practical understanding of how logistic regression works and different methods for model evaluation. Feel free to use the chapter markers to skip around. That said, let's get started. The data we are using today was downloaded from Kaggle website. You'll find the link in the description below. Download and save the unzipped file in any local folder. You can rename it as data. For this video, we'll be coding in Google Colab. Many popular libraries are pre-installed, so we can save on environment setup time. We can store the project in Google Drive and access it directly. All you need is a free Google Drive account. Visit Google Drive and log into your account. Create a new folder by the name Mobile Price Range Classification. This is our project folder. From desktop, drag and drop our new data folder into the Google Drive project. While it is uploading, let's create a new Google Colab notebook and rename the title as Mobile Price Range Classification V1 for version 1. We have our runtime getting connected. Let's mount Google Drive. If this is your first time doing this, you might need to authenticate Google Drive. Let's check out our Google Drive folder. I'll have to refresh to see the new file name. Okay, confirm our data is all set. Back in the notebook, note that Google Drive is already mounted. That's it. That's all the setup we need and we are ready to code. All right, let's start by creating a markdown cell for title and description of the project, making sure we document our project well right from the start. Import the basic libraries that we'll need. Printing out a simple timestamp helps us keep track of the updates. We'll come back to the cell and update as we progress in our project. It's a good idea to declare constants at the beginning of the notebook. It makes it easier to track them later. For now, create one for the path of our data folder. Time to import data. We'll use only the training dataset for this project. Let's call it train dataset and use pandas read CSV to do so. Make sure to check the shape of our data frame. It should match the number of rows and columns from the CSV file. Take a better look at the structure by using the head and tail methods. We are ready to begin EDA to understand our data better. Before that, create a copy of the original dataset to make sure our changes are restricted to the copy and we can refer to the original anytime. Quick tip, you've noticed that I create many section headers like this. It's very useful, especially when the code gets longer. On the left panel, you can easily switch between sections without having to scroll the entire notebook. After creating a copy, always take a look at it to make sure we are using the right copy. We haven't yet seen all the columns of our data frame. Head and tail hide some of the columns in the middle like this. We can do that by transposing the data frame like so. Info shows us the data types of all the columns as well as any non-null values. Describe is another way to check out the numerical data. It shows the mean, standard deviation, min, max, etc. This is when we usually handle data cleaning. So we'll check for null values like this. Our data is already clean and we can confirm it by doing a sum of all the column sums. That should be 0. Let's analyze some of the features. This is univariate because we are viewing a single category of data at a time to get a lay of the data. Start with the target, which is price range. Check its value counts. Forgot the S there. Quick look. Our data looks evenly distributed. Let's try a visual by using count plot. Distribution of samples by price range. Let's quickly print out the column so we can just copy and paste. So next is battery power. Note that writing it like this is the same as this if there are no spaces in the column names. Battery power seems to be in a wide range of values, and value counts will output many lines. So let's just look at the first 20 or 30 lines. Have a look at the minimum and maximum. So battery size ranges from 501 to almost 2000 in our data set. Let's take a peek at the rows with 1998. Only one sample. How about the lowest battery size? 2 rows. What's next? Bluetooth. It makes sense to do value counts for categorical data because there's only a limited number of categories and it's easier to see the distribution. In the interest of time, I'll take a shortcut and copy the notes that I have already taken and I'll paste it in the notebook description. You can get a good understanding of our features from this. Well, now we have our columns and a better understanding of the features. We can start plotting them visually. But first, separate the features into categorical and numeric. Make a list of categorical features. We'll choose the ones with binary values here. Next is numeric. You can just simply take the columns and remove the categorical features from it. Remember to exclude the last column, which is our target. Right, time to start plotting. Histograms for numeric features is a good starting point. We'll be able to gain insights from this. A quick look shows us that the FC data, which is front camera in megapixels, looks very skewed. We might pay special attention to this later. Screen width and pixel height are uneven too. Well, next up, let's do count plots for categorical data. We'll enumerate the list and loop through so that we can plot the subplots. I see a bit of overlap. I think tight layout should take care of that. Neat. Most of the categorical features are evenly distributed. Well, next up, bivariate analysis. That will be us comparing two different features. We'll plot all of our features against the target, which is price range. Let's handle categorical first. It's very similar to the previous step, except now we have added hue to differentiate price range with different colors. As expected, data is evenly distributed pretty much, except for 3D, which is very understandable. Next will be numeric features, and we'll use box plots for them. Very similar code here. Box plot with price range in x-axis and feature in y-axis. Too compact. Let's increase the height. That's better. Most of the box plots are evenly distributed. It seems that the front camera plot is showing some unevenness. There are many outliers here at the top. It indicates that there are some phones with very high front camera megapixels is found in all price ranges. Models with advanced camera features, right? A low box and low whiskers like this suggests that most of the phones in each price range have relatively lower megapixels. High variability can make it challenging for models to use this feature effectively without additional context. We can further analyze this. We can group the FC data by price ranges and then use the describe method to show summary statistics like mean, standard deviation, etc. The mean value increases slightly with price range. Phones in higher price ranges have, on average, slightly higher front camera megapixels. Standard deviation is pretty high, meaning there is high variability. That could also be because of the outliers. A correlation matrix shows us the relationship between two variables, the strength and the direction of their relationship. Positive 1 means strong correlation, and a negative 1 means strong negative correlation, which is an inverse relationship between the two variables. The diagonal values represent the correlation of each feature with itself. So the diagonal values are always 1, right? It is a reference point showing a linear relationship. We can see here that FC and price range has very low correlation. We can also use scatter plots to visualize the relationship between these two variables. There is no apparent linear relationship between the two variables. The significant variability might suggest that FC alone is not a strong predictor of price range. We might have to handle the outliers, which will be part of a more advanced tutorial, and hence we won't be handling it today. Okay, back to our box plots. RAM versus price range also shows a high correlation here. We can compute the correlation coefficient between RAM and price range to measure the strength of their relationship. As we can see, the correlation here is almost 1, which is very strong. The visual observation from the box plot is a good start, but we need advanced techniques like feature importance from a model. For example, it can give you a clearer picture of how much each feature like RAM or front camera resolution can contribute to actually predicting the price range. Okay, next up, multivariate analysis. We'll use more than 2 features and compare them. Let's start with a correlation matrix to compare all of our features at once. We can see that our features are measured against each other, but the numbers don't really look like much, right? Let's visualize this with a heat map. Here we go. Most values look blue here because our lowest values are all around 0 and we don't really have many negative numbers here. So our lowest seems to be only 0.05. So let's tweak the code a bit to show us blue only when there is negative. That should be cleaner. That should do. Good, looking good now. And let's add some lines to separate the cells. Make it a bit thinner. Beautiful. Right, the diagonal values are in red, being the highest value here, but they are not the focus of our analysis. We are interested in the off-diagonal values here, showing the correlation between different features. As we have already seen, the correlation between RAM and price range is 0.917. Screen height and screen width, 0.506 here, seems to be moderately correlated, which makes sense, right? Since larger screens would likely have both height and width increased. Pixel height and width, 0.511. Same goes for pixel height and width, right? 3G and 4G, 0.584. Right, devices or areas, regions that have 3G capability are somewhat likely to have 4G capability, but not always. Newer devices are more likely to support both technologies. FC and PC, 0.645. The correlation between FC and PC, which is primary camera, front camera and primary camera indicates that devices with a higher front camera resolution also tend to have higher primary camera resolution. Although this relationship isn't completely direct since it's only 0.64 and not closer to 1. For feature pairs with correlation near zero, there's no significant linear relationship, meaning these features do not vary together in any predictable way. We can visualize pairwise relationships between features using pair plots. We'll choose some features that seem to carry a linear relationship with one another. We'll just choose these for now. Price range as the hue. Let's analyze each of them. Diagonal plots show the relationship between each feature and the price range. The distribution show that higher values are generally associated with higher price ranges, the highest price range being the darkest here. Features like RAM, battery power, and pixel width are good indicators of price range. Higher RAM values, that's towards the right, tend to have higher battery power values. Higher price ranges, which are in darker shades, are concentrated in the upper right region here, indicating that devices with more RAM and higher battery power are more expensive. We'll wrap up EDA for now and we'll take note of some key findings. We noticed that our data was pre-processed, didn't have any missing values, and they were all numeric. But they do have certain different scales when it comes to values. For example, some of our features are just zeros and ones, where others range between 2 to 4 digit figures. This can be a problem for some models to train because the steps taken by the model to handle each feature varies according to the scale of the data the model sees. Meaning, some of our features can end up getting more time to train or more weightage than others. And this unevenness can cause issues with model training. We'll keep this in mind and move on. A few other things that we have noticed, but given the beginner friendly nature of our video, we won't be handling them today, but it's important that we understand this. Front camera data is skewed, have many outliers, and the standard deviation is high. This suggests high variance, but its correlation with price range is low. This can affect the learning process and distort predictions. We have noticed strong and weak correlations between features, and we should be handling them by doing feature engineering. We will learn how to handle these features in a different segment when we look at advanced techniques like feature engineering. Well, after that long EDA process, we are finally ready to build and evaluate our model. A simple logistic regression, a popular choice for many classification tasks. We'll assess the model's performance to see how well it can predict the price range of mobile devices and identify areas for potential improvement. Let's start by taking a look at the data frame that we have been working with. Everything seems to be in order. Okay, splitting data. Quick note, we'll train our model using the training data. We'll use the target column, which is price range in our case, as labels to fit the model with. After training, we will be able to evaluate the model using a test data set by comparing the new predicted labels against the truth labels. In our case, we have a test set, but as it didn't come with truth labels, we won't be using that. We'll create our own validation set using a part of our training set. But first, we'll separate features and labels. Remember that our training set is just the features without price range labels. So let's call it X. Labels will be called Y. Let's confirm the shape of X and Y. Good. Now it's time to split X and Y into training and test subsets. We'll use train test split from scikit-learn's model selection. It is not accessible yet because we haven't imported it. Let's go back to the import section and do it. Neat. The train test split function accepts features and labels along with the test size, which determines the percentage of data to be randomly shuffled and included in the test subset, validation subset in our case. We'll also use the random state so that the randomly generated data points are reproducible. It returns a list containing train test splits, which we will assign as train and val, like so. Let's take a look at the shapes of the items we just assigned. Since we used 0.2 as the test size, 80% of our data should be xtrain and 20%, which is 400, is in xval. Good. With that done, it is time to start building, training, and evaluating the model. But first, let's understand what logistic regression is. This simple yet powerful tool models the probability of different categories, making it an ideal starting point for understanding classification in machine learning. The term regression comes from its roots in regression analysis, but since its outcome is categorical, we use it for classification tasks. It is a linear model, which means it makes predictions by combining the input features in a specific way. Each feature is multiplied by a certain weight, and then all these weighted values are added together to form a single number. This number is then passed through the sigmoid function to map it to a probability. It is used primarily for binary classification, where the data points are classified into one or two classes. For example, predicting whether an email is spam or not spam, or whether a customer will buy a product or not. We can extend it to handle multiple classes using softmax function. This function outputs probabilities for each possible class rather than just a binary outcome like in the sigmoid function. This is called multinomial logistic regression, and that's what we'll be doing in this project. Well, we are using logistic regression model and we'll call it CLF for classifier. It is not yet accessible. We'll need to import it from scikit-learn's linear model module. We'll use the same random state we used during the data split, but we'll leave all the other parameters as default. Then we'll fit the model, which is a process when the model learns patterns from the data along with labels. These patterns are used to make predictions when presented with unseen data, which is our validation data set. We have this warning, and it's called convergence warning. LBFGS failed to converge, total number of iterations reached. Right, if we take a look at the doc string for definition, we can see max iter 100 by default, solver, LBFGS is default solver. The default ones are used since we didn't pass these parameters. Solver is an algorithm used to optimize model parameters, and it minimizes errors in predictions. This warning means that our model has failed to find the optimal solution in the given number of iterations. The solver couldn't minimize the error enough, and the model won't perform well while predicting. We see a few suggestions here. One, we can increase the number of iterations using max iter. Two, we can scale the data. Three, try alternative solver option. Okay, let's try the first two suggestions. And if they don't work, we'll come back for the next one. Okay, trying max iter. The default max iter was 100. Let's increase it to 1000. Let's see if this works. Nope, that didn't resolve the warning. So we'll move on to the next suggestion. But feel free to pause the video and experiment with different values for max eta, like 200, 400, etc. Next, scaling the data. Okay, we did talk about this earlier at the end of EDA. We noticed the difference in scale between our features, some of them zeros and ones, and some of them 2 or 4 digit figures. We took note that it might affect the model's ability. Let's see how we can scale the data or normalize it. Let's take a look at the original data first. We'll use a simple standard scaler for this purpose. We need to import it so that it will be accessible. It's in scikit-learn's pre-processing module. Okay, let's fit the scaler using the training data. This is how it learns the parameters like mean, standard deviation, etc. to decide how best to scale the data. Since we have already split data into train and validation sets, we have to transform them separately. We'll use a scaler that we have already fed using the training dataset. It will transform them into a normalized dataset. Let's take a look at the scaled data. Okay, what's happened here is that our data is adjusted, somewhat like stretched or maybe squeezed so that all features are on a similar scale. This makes it easier for the model to learn from them. After scaling, the data points still retain the shape and relationships. It's just that the values are transformed to be more uniform. Right. Let's try this scaled data. We need to instantiate the model again because we have already tried to tune some parameters earlier. For this tutorial, we want to use the default parameters as much as possible. Let's fit the model with the scale data and pass the Y labels. Right, that worked. Now that we have fixed the convergence warning by scaling our data, our model is ready to make predictions. We'll use the predict method and pass unseen data, which is in our case xval scaled. Remember to use the scaled version. Prediction and evaluation should always use data in the same formats that was used for fitting. Let's check out the shape. 400. Where have we seen this number before? Yes, it's the number of samples in validation set. Check out what's in this. Okay, it's an array of values 0, 1, 2, or 3, similar to what our labels look like. Given the validation dataset without labels, the model has made these predictions to the data, classifying them as one of the 4 price ranges. One quick way to check how the model is performing is by scoring it. It returns the representation of the model's accuracy or performance. In our case, it gives us the percentage of correct predictions out of all the predictions the model has made. If the model correctly predicts 90 out of 100 instances, the accuracy will be 0.9 or 90%. The best possible score is 1.0, and the score can also be negative if the model is unpredictable or it hasn't been trained properly. 0.975. So our model seems to have been trained well, but let's evaluate further by using some really important classification methods. Before beginning, let's import classification report and confusion metrics from scikit-learn's metrics module. While we are here, let's also import confusion metrics display. We'll see it used in a moment. Right, classification report. Pass the truth labels and predictor labels to break down the model's performance across each class. Right, we'll take a detailed look at this in a minute. Before that, let's look at the confusion metrics too. Okay, it gives us a visual way to understand where our model is making correct predictions and where it might be making mistakes. Let's examine them in detail. First is classification report. Precision is the proportion of positive identifications that were actually correct. It means it's the measure of accuracy of the positive predictions. Next is recall. Recall is also called sensitivity or true positive rate. It measures the proportion of actual positives that were correctly identified. Next is F score, which is the harmonic mean of precision and recall. It's a balanced measure that takes both false positives and false negatives into account to calculate this. We also have the support column, which is the number of samples of each class in the dataset. Okay, next is the confusion matrix. It is a square table that compares the actual values with the predicted values. The rows represent actual class while the columns represent predicted class. Let's analyze the classification report and confusion matrix side by side to see how they relate to each other. On the left-hand side, we have classification report, which shows us key metrics like precision, recall, and F-score for each class. On the right side, we have confusion matrix, which gives us the visual representation of where our model is getting things right or wrong. Let's start with class 0. In the classification report, we see a precision of 1.0, a recall of 0.96, and F-score of 0.98. Now let's see how these numbers are reflected in the confusion matrix. We have the number 101. This represents true positives, TP, what the model correctly predicted as class 0. 4 instances where the model incorrectly predicted class 0 as class 1. These are false negatives. We have high precision and high recall for class 0. This makes sense because most of the predictions were correct with only a few misclassifications. Let's move on to class 1. Precision 0.94 and recall is 1, resulting in an F-score of 0.97. In the confusion matrix, 91 instances of class 1 were correctly predicted. This explains the perfect recall. Precision is lower because 4 instances of class 0 were incorrectly predicted as class 1, which is false positive. Next, class 2. 87 correct predictions for class 2 makes the precision almost perfect, which is 0.99. Recall is slightly lower because 2 samples of class 0 were predicted as class 1 and 3 instances where it was predicted as class 3. Move on to class 3. It has a precision of 0.97. Recall is almost perfect, 0.99. Results in an F-score of 0.98. 111 correct predictions with only one instance misclassified as class 2, which is why both precision and recall are so high in this case. By comparing these tools side by side, we get a complete picture of how well our classification model is performing. Overall, the model performed well with a high accuracy of 0.97 and a balance of precision and recall, as seen in the classification report and confusion matrix. Further improvements could be made. We could try different algorithms, tune hyperparameters, or apply feature engineering. But for now, we'll wrap up this tutorial with these findings. Well, today we successfully built a logistic regression model to predict mobile phone price ranges. We used pre-cleaned data, but we conducted a detailed exploratory data analysis EDA and identified key adjustments to train the model well. We scaled our data and we built a logistic regression model. We examined the classification report and confusion matrix in detail to understand our model's performance. You can find links for this completed notebook and the dataset source in the description below. In upcoming tutorials, we'll dive into more advanced topics, including hyperparameter tuning, feature engineering, and many other machine learning techniques. If you enjoyed this video, please like and subscribe to the channel. Let us know in the comments below if you have any questions or any suggestions for future content. Thanks for watching. See you in the next video.